S is a supremum of A, and S prime, well, it's a supremum, but as a supremum, it's also an upper bound, right? And that's the property that we're interested in here when we're proving this. S prime is an upper bound of A. What inequality do we get?
S is less than 3.
Yes. Again, if you want to think about it as the least upper bound, right? We've got this guy here, and we've got an upper bound. So that means that the supremum has to be less than or equal to that upper bound. But now what?
There's S prime is the supremum of A, and S is an upper bound of A.
Right. In other words,
S is less than or equal to A.
yes, and so the proof is really, I mean, you're absolutely right, but we'll just say that it's similar, right? Because we didn't use anything special about S and S prime. They're just two suprema. Okay? Similarly, I have to have at least one large cup of tea before I can say that. S prime is less than or equal to S. And this is, now that we're starting to do things that involve inequalities a lot, you know that this is one good way to prove two things are equal. It's like proving two sets are equal, right? What do? You prove one is contained in the other, and vice versa. Now sometimes you can do an argument where you say something is in this set if and only if it's in that set, and sometimes you can do equalities in that way also. But very often it's useful to prove inequalities in opposite directions to show two things are equal. And it is also true, just like remember when we were proving things are subsets, every now and then, and the farther along you get, it will be more and more true. Sometimes one of these is way easier than the other, right? I mean, sometimes one of them is almost given for free, and then you have to work really, really hard to get the opposite inequality. Okay, so in that case, you don't have a proof going forwards and backwards easily, right? Now, for this one, of course, it's the exact same proof. Just go through it and take the prime off one of the S's and put it on the other. Okay? So this tells us S equals S prime. So, since we've shown it's unique, we can go ahead and give it a name that depends only on S. Okay, so if the, right, so now we can change articles, right? If the, because there's only one, supremum of A exists, we call it sup A, okay? And that's a long U, right? As in supremum, which comes from Latin. Likewise, if A has a maximum, then it's unique, of course, because a maximum is a supremum, right? It's a supremum that happens to be in the set. So there couldn't be two maxima, because if there were two maxima, then there would be two suprema, and that can't happen, okay? There was a thing on Car Talk once. What is the? I think there are two automobiles whose names are plurals, okay? And you've just heard one of them. Okay, we call it max A. I don't remember what the other one was, but I remember this one just because, of course, I use it all the time. Okay, any questions about all these definitions now and this particular lemma? Now you know there is one and only one of these suprema. And there is a similar statement for infimum. Just replace supremum by infimum. And you could go through the exact same proof. Okay, and in fact in that case you wouldn't even have to, Well, yes, you would. You'd have to reverse the inequalities there, but you know, again, it doesn't matter which is S and S prime. Okay, so you'd have to change the names of what you pick up. Okay, let's do a simple example. Oh, sorry. Let's introduce the completeness actually first. No, do an example. Let's suppose that A is equal to a set containing two elements in our ordered field. What do you think is true about this set in terms of sups, infs, maxes, mins? Well, first of all, let's make sure they're different. So we'll suppose if they're different, then one of them is going to be less than or equal to the other, right? So we'll just say suppose x is less than or equal to y. Well, actually, we'll allow even the case that they're equal there. But certainly that's true. One of them is less than or equal to the other. What do you think is true about this?
One is the superior, one is the maximum, one is the minimum.
Yes, and which is which?
Y is greater, so Y is
Y is the maximum, x is the minimum. Okay, that seems entirely obvious, right? Because you've dealt with sets containing two things, and the big one is the maximum, and the small one is the minimum, right? Okay, but we're actually going to prove this, okay? To show that you have to be just a little careful about these things. It's fairly simple, okay? So we're going to show that x, well, actually, we're just going to show y equals maximum of A, and then similarly, x equals minimum of A. So, to show that y is the maximum of A, we basically have to do three things, right? What are the three things? What's the first thing we have to show? That it's an upper bound. Next thing, supremum. And third thing, in this case it's pretty trivial, but we have to show it's in the set to make it a maximum. Okay? Okay, so. Okay, so now, of course, let is a little bit silly because we have our two things listed out, okay? So I said usually it's going to be open line, but now we just have to check two things since they're right up there. So since what do we have? What are the two things we need to check?
upper bound.
Yes, so what are the two things we have to check to show it's an upper bound?
Greater than or equal to.
What's greater than or equal to what?
Y is greater than A equal to any element in the set A.
Okay, and what are the possibilities for sets in A?
X and Y.
So what's the first thing I write down?
Y is greater than
X less than or equal, okay. X is less than or equal to Y, let's do it that way, okay. And,
Y.
yeah, we'll just go ahead and say Y less than or equal to Y. So I've checked the two possibilities in there. So Y is an upper bound. Of A. Okay, what's the next thing I need to check?
Y is the least.
Soup. Okay, so what's my opening line to check that something is a soup? Yeah, let M be an upper bound. And again, in this case, the proofs are really simple, but the opening lines are all the same. And so it's the usual thing. If you just know where to start in a lot of these, you can usually find your way through it. And when you get stuck on these, it'll usually be because you're not starting in the right place. You're not starting with the statement that you need to start with, or you're not finishing with what you need to finish with. Okay, upper bound of A, right? Good opening line. What do I need to show?
It must be X less than or equal to M and Y.
No, we're assuming we already got an upper bound. So we don't need to show it's an upper bound. We've got an upper bound. What do we need to show about this upper bound?
Y is less than M.
Yes, okay. But, okay, since y is an element of A and M is an upper bound of A, y is less than or equal to M. Okay, so this shows y equal sup of A, right? And what's the last line then? Last thing I need to say about y?
Y is an element of
Yeah, since y is an element of A, y equals max A. And I'm done. Okay, now again, this is the thing where you might say it's obvious. Well, okay, fine. If you want to claim it's obvious, you need to be able to do exactly what I just did there. In fact, it's not even a one-line proof. Well, each step is a one-line proof if you want. Okay, yes.
How do you get to y is less than or equal to m?
Okay, what is M?
M is an upper bound
And where is upper bound of?
set A.
And where is Y?
Y, what do you mean where is it?
Where is it?
In A.
It's in A. And if M is an upper bound of A, what can you say about anything in A? It's less than or equal to M. Does that make sense? Right? I mean, the definition of upper bound is that if you pick up anything in the set, it's less than or equal to it. So we picked M is an upper bound of A. Y is in A. So Y has to be less than or equal to M. That's the definition of upper bound.
Okay.
So, and again, the part of the problem here is that it's almost too simple, right? But even simple things, you should be able to write them down cleanly and carefully. So this is a great starting point, all right, for you when you go home to start working on your homework, which probably won't happen for a little while with this homework set, right? You need to start with that. Okay, so this is a useful thing, and in fact, as you can imagine, if you have any finite set, right, the biggest one in there is going to be the max. Well, the biggest one for you is the max, and the smallest one is the min, okay? And so, but we can't prove that. That would require something called induction that we'll talk about later, but you get the idea, okay? But we are going to need max and min of two things for some of the arguments that happen in here. Okay, so having done all that, let's go with the completeness axiom. So if A subset of F is non-empty and bounded above sup A exists. Okay, so here we go, right? We're not actually proving this because we can't. Because as you know, in the rational numbers, if you take, for example, in the rational numbers, you take A equal the set of all x, an element of the rational numbers, that's Q, as in quotient if you want to think of it that way, such that x is less than the square root of 2. Okay, we'll prove things like this later, but that doesn't have a supremum, right? In Q, because the square root of 2 is not in there. Again, I'm not proving any of this, I'm just letting you know that the rational numbers don't satisfy this axiom. Okay? In fact, if you take any open interval where the right-hand endpoint is not in there, right, but it's an irrational, there's no sup of that in the rational numbers. So, and again, I'm not proving anything here, I'm just trying to help you absorb this idea, right? So Q is not complete. Again, we can't prove that now, we will prove it later actually, okay? We'll prove the square root of 2 is not a rational number, and hopefully we're at the point where society won't drown us, although I sometimes wonder. Okay, so for doing so. Okay, and this is not unique, but there is actually, this is a hard theorem. which we will not prove, there is a unique, complete, ordered field. And we will call that ordered field R. That's the name we're going to give it, and it's the real numbers as you've always known it. And this is the last axiom that you need to do everything that you have ever done in mathematics. Okay, in calculus and all that. Every single theorem that you used in calculus to do anything can be proved from all the axioms we now have. And if you take, for example, advanced calculus, then if we take the honors version anyway, then one of the things that you do in there is to prove much, much more of what you do in calculus. And then it becomes a field known as analysis, real analysis for real numbers. There's also complex analysis for complex numbers, right? But that's where you prove things that are really dependent on things like approximation and so on. That's really what analysis is. Whereas algebra, which goes way beyond what you learned, have learned so far, is something that just uses axioms like the field axioms for algebra.